Inefficiency of equilibrium as a design metric. Motivation. In the previous section, we studied four natural network examples. The game was given and immutable in all of these examples, and the only question involved the quality of its equilibria. While most work on the inefficiency of equilibria has been of this form, the flexibility of the framework presented in section 17.1.2 begs a more general question. How can we design a game or modify an existing game to minimize the inefficiency of its equilibria? This question is especially crucial in settings where equilibria are unacceptably inefficient, but directly imposing an optimal solution is impractical. Example questions of this type include the following. Among a given class of mechanisms, which one induces a game with the best price of anarchy? Quantitatively, what is this best possible price of anarchy? Given a game and a restricted set of options for influencing its equilibrium, which option improves the price of anarchy by the maximum possible amount? How large is the improvement using the measures of inefficiency described in section 17.1.2? We can rigorously compare the performance of different solutions and quantify the efficiency loss obtained by an optimal solution. And these goals are conceptually the same as those of algorithmic mechanism design, studied in part 2 of this book. However, much of the work we describe below and in the notes, section 17.4, differs from the bulk of the material in part 2 in three technical respects. First, while part 2 largely concerns the design of strategy-proof mechanisms in which truthful revelation is a dominant strategy for every player, we study the equilibria of mechanisms that are not generally strategy-proof, and for example, in the proportional sharing mechanism described in section 17.2.4, the strategy space of a player non-negative bits does not coincide with its type space utility functions, and no player has a dominant strategy. These differences are typically motivated by practical considerations, as we discussed in section 17.3.2. And second, some of the research described in section 17.4 considers games without private preferences. In these cases, the design problem is non-trivial because the mechanism designer lacks full control over the allocation of resources, optimally influencing traffic in a selfish routing network by pricing the network agencies is one example of such a problem. Third, in much of the work discussed in section 17.4, the problem is not to design a good mechanism from scratch, but rather to leverage a limited amount of power to improve the equilibria of a given game as much as possible. 17.3.2, an example, the proportional sharing mechanism. We now informally described one example of how the inefficiency of equilibria can serve as a design metric. Chapter 21 discusses the Chapter 21 discusses the following result in greater detail, and section 17.4 discusses additional examples. Recall the resource allocation games of section 17.2.4 where n players compete for a divisible link with a capacity C. And we study the proportional sharing mechanism in which each player I submits a bit Bi to the mechanism allocates all of the bandwidth to the players in proportional to their bits. And every player then pays its bit. This mechanism induces a non-cooperative game, as proved in chapter 21. The price of anarchy of every such game is at least 3/4. We next strive to surpass this efficiency guarantee and ask, How can we modify the mechanism so that the price of anarchy is always even closer to 1? The answer to this question depends crucially on the class of mechanisms that we are willing to consider. If we impose no restrictions on the allowable mechanisms, then a version of the BCG mechanism, see Chapter 9, always induces a game for which the price of anarchy equals 1. And however, this solution is more complicated than the proportional sharing mechanism in two ways. First, the communication from the players to the mechanism is more involved. Each player must submit a representation of its entire utility function as opposed to a single bit. Second, the communication from the mechanism back to the players is also more complicated in the following sense. In the proportional sharing mechanism, allocations can be completely summarized by the bips in a single additional parameter, the price of bandwidth. And to see this, consider a bit vector b1, b2, b3, and bn for a link with capacity C. Set a price p equals to b over c, where b is the sum of the bips and c is the capacity. So if we set a price p equals to b over c, the proportional allocation to each player I is then simply its bit bi divided by this price. And while the allocations of the BCG mechanism can be similarly interpreted in terms of prices, different players are generally allocated bandwidth according to different prices, and the simplicity of the proportional sharing mechanism that the communication both to and from the mechanism is limited makes it particularly suitable for implementation in large communication networks. Is there a mechanism that retains these appealing properties and has strictly smaller, worst-case efficiency loss? Chapter 21 shows that the answer is no. For appropriate definitions of bounded communication, every equal simple mechanism can induce a game that has a price of anarchy of at most 3/4. The proportional sharing mechanism is therefore optimal among all mechanisms, meeting natural, desirable implementation constraints. Notes: the observations that self-interested behavior can lead to a socially inefficient outcome is an old one. See, for example, Dewey, 1986, Rappaport, and Treman, 1964, and the references therein. The idea of quantifying the inefficiency of equilibria using an objective function and an approximation measure is much newer. The concept of the price of anarchy originated from Koutsalpius and Papadimitriou, 1999, where it was called the coordination ratio. Koutsalpius and Papadimitriou studied generalizations of the scheduling games described in section 17.2.3. Papadimitriou, 2001, introduced the term the price of anarchy. The price of stability was first studied in Scholz and Steyer, Moses, 2003. The terminology is from Anshelovich et al., 2004, and several earlier works, and in particular Mason, 1985, anticipated these concepts. See also Sather, Watt, and Williams, 1989, and Maulin and Schenker, 2001, who studied additive notions of efficiency loss in mechanism design applications. The measures of inefficiency discussed in section 17.1 are similar to and motivated by several well-established concepts in theoretical computer science. One example is the approximation ratio of a heuristic for a typically NP-hard optimization problem, defined as the worst ratio between the objective function value of the solution produced by the heuristic and that of an optimal solution from the Verisani, 2001. While the approximation ratio measures the worst case loss in solution quality due to insufficient computational effort, the price of anarchy measures the worst case loss arising from insufficient ability or willingness to control and coordinate the actions of selfish individuals. the novel notions of equilibrium outcomes alluded to in section 17.1.2 are described in Marocni and Vita 2004 and Gomez et al. 2005. Tenenhaus 2002 also proposed relaxing the assumption that players reach a natural equilibrium and examining the consequences for the players' payoffs. The inefficiency of other equilibrium concepts has also been studied. See work by Christodoulou and Kaltsopias 2005 on correlated equilibria, section 1.5, Endelman et al. 2007 on strong natural equilibria, section 1.6, and Heyrep et al. 2006 on equilibria in the presence of coalitions of players. Pigau's example 70.1, is from Pigau 1920. Selfish routing networks and their equilibria were defined formally by Wardrop 1952 and Bachman et al. 1956. The potential function method originates in Becken et al. 1956 and was later developed by Rosenthal 1973, Monderer and Shapley 1986, Rovgarden and Tardos 2002, and Anshelevich et al. 2004. Shapley network design games were first studied by Anshelevich et al. 2004. An example 17.3 is from Anshelevich et al. 2004. Example 17.2 was given in an earlier paper by Anshelevich et al. 2003. The scheduling games of section 17.2.3 and example 17.4 are due to Kapselpias and Papadimitri 1999. See Moltwani and Rafavan 1995 for a discussion of the balls into bins problem. The proportional sharing mechanism is due to Kelly 1997, and example 17.6 is from Johari and Tsitsiklis 2004. For further references on the four network models of section 17.2, see chapters 18 to 21. The results mentioned in section 17.3.2 are from Johari and Tsitsiklis 2006 and are discussed in future detail in chapter 21. Chapter 21 also covers variants of the BCG mechanism in which users submit only a single bit rather than an entire utility function. These mechanisms are not and cannot be single price in the sense of section 17.3.2. However, we conclude these notes with examples of how measures of inefficiency have been used to compare different mechanisms and different strategies for influencing equilibria in the network models explored in section 7.2, and several approaches to improving the equilibria of a selfish routing network have been considered, including pricing the network addresses and routing a small fraction of the traffic in a centralized manner. The goal is then to leverage the limited amount of design power to minimize the price of anarchy. For details on this literature, see Rovgarden 2005, chapters 5 to 6, and the references therein. Motivated by the network design games of section 70.2.2 and example 70.3, Chang et al. 2007 studied how to design cost-sharing methods to minimize the inefficiency of equilibria in the resulting network game. One of the contributions in Chen et al. 2007 is an analog of the result described in section 7.3.2 for resource allocation mechanisms among all cost-sharing methods that are oblivious to the network structure in a certain precise sense. The Shapley cost-sharing method of section 70.2.2 minimizes the worst-case price of stability. On the other hand, cost-sharing methods that can leverage information about the network topology can outperform Shapley cost-sharing methods, Chen et al. 2007. Finally, for the scheduling games of section 7.2.3, Christodoulou et al. 2004 and Imorlica et al. 2005. design machine scheduling policies to improve the efficiency of Equilibria. Informally, such a policy can be used to prioritize one player over another, thereby causing different players to incur different costs on a common machine, as shown in the Christodoulou et al. 2004 and in Mordecai et al. 2005. Even very simple scheduling policies reduced the price of anarchy from logarithmic in the number of machines, example 17.4, to a small constant.